Fever often causes discomfort, leading many to take medication to reduce it. However, this practice may not be entirely advisable. Scientifically, fever has been recognized as one of the ancient mechanisms employed by the body to combat illnesses. But what exactly constitutes a fever? How does it enhance the body's immune responses, and is it prudent to use medication to counteract it? The heat of life on Earth. Life thrives within an extremely narrow temperature range, from the frigid depths of 10 degrees Celsius in deep cold pools to the scorching 120 degrees Celsius in hydrothermal vents. Deviating outside this range typically results in death. Every living organism, whether a complex animal or a microscopic microbe, has an optimal temperature range where its biological processes function most efficiently, alongside a stress zone that can be endured for limited periods. For humans, this ideal temperature is approximately 37 degrees Celsius, 98. 6 degrees Fahrenheit, a state where cellular machinery operates at peak efficiency, enabling the body to adapt effectively to its ecological niche. As warm-blooded creatures, humans expend significant energy to maintain this temperature, which might seem inefficient at first glance. However, this elevated thermal state could serve as a defensive adaptation, as it renders the body nearly impervious to fungal infections, a major threat to many other species. Most cold-blooded animals and their internal environments are prone to fungal infestations, but humans are shielded by their relatively high body temperature. This leads us to the concept of fever. When a pathogen attempts to infect an organism, the body's internal environment becomes a battleground. Fever acts as a form of defensive climate change, elevating the host's temperature beyond the ideal range for invading microbes, making the environment inhospitable. This mechanism has evolved over at least 600 million years and is widespread across the animal kingdom. Many species raise their core body temperature when ill. Fish migrate to warmer waters, lizards bask in sunlight, and bees increase the temperature of their hives. As a warm-blooded mammal, humans possess a more extreme physiological response. Let's explore the process when your body temperature surges. When your blood turns into lava, your body is simultaneously attacked by bacteria and viruses, which launch a coordinated invasion. To slow this onslaught, the body initiates a critical first-line defense: fever. This process is triggered by a group of signaling molecules known as pyrogens, often referred to as heat creators. These chemicals circulate through the bloodstream, reaching the brain where specialized receptors activate the body's internal thermostat. The initial response is shivering, as skeletal muscles contract rapidly to generate heat in the core. At the same time, blood vessels near the skin constrict, limiting heat loss through the surface. The result is a dramatic temperature increase. While your skin feels cold, your internal organs are subjected to intense thermal stress. Fever is a systemic, whole-body reaction that demands substantial energy. For each degree Celsius the body temperature rises, energy expenditure increases by approximately 10% to sustain vital functions. Additionally, fever compels the body to rest, conserving energy for the immune system to wage its battle. Returning to the battlefield, when pathogens enter the body, they initially operate covertly. However, fever disrupts their strategy, forcing them into a high-stress, high-production mode. Their goal is rapid replication, which requires abundant resources and generates immense cellular strain. Imagine attempting to run a marathon while consuming a lavish meal and simultaneously giving birth, an impossible feat for any organism. The last thing bacteria need is additional stress, yet fever exacerbates their challenges. The immune system further compounds this by triggering inflammation, flooding the affected area with fluids, attack proteins, and immune cells. The situation becomes increasingly hostile. Fever intensifies this pressure, pushing bacteria beyond their thermal limits. The heat can cause cellular damage, membrane rupture, DNA degradation, and impaired protein synthesis, making survival increasingly unlikely. But how does this not harm the host cells? Indeed, fever is stressful for all cellular systems, except the immune response. During fever, neutrophils are mobilized more rapidly, macrophages and dendritic cells become more efficient at eliminating pathogens, and killer cells perform better. Additionally, fever restricts the availability of critical nutrients like iron, glucose, and glutamine, creating a nutritional scarcity on the battlefield. Viruses, which have already infected millions of cells, face even greater challenges, as they are inherently sensitive to heat. For instance, the rhinovirus, responsible for the common cold, can only infect the respiratory tract because it remains significantly cooler than the rest of the body, even in the absence of fever. The elevated temperature also wreaks havoc on the virus-infected cells, which are already under immense stress from producing new viral particles. As heat intensifies, these cells experience a crisis, triggering the production of heat shock proteins, HSPs, to initiate repairs. However, this is a double-edged sword. HSPs are also produced by healthy cells under stress, but an excessive amount signals severe cellular distress, prompting the immune system to eliminate the affected cells. Natural killer cells and killer T cells are attracted to HSPs and target infected cells, effectively eradicating both the pathogens and their host. Thus, the very act of self-preservation by infected cells leads to their destruction. Despite the efficacy of fever as an immune weapon, why haven't pathogens evolved resistance to it? A compelling explanation lies in the evolutionary dynamics of fever. If pathogens survive fever, natural selection drives their adaptation. Over time, individuals better suited to withstand heat proliferate, creating a population that thrives in warmer conditions. However, this adaptation becomes a disadvantage when targeting new hosts, as humans, who are typically cooler, become less susceptible. The heat-resistant microbes now face competition from their cold-adapted counterparts, which are more effective at infecting healthy hosts. This creates an evolutionary paradox without a clear resolution. To circumvent this, highly virulent pathogens like the measles virus employ hit-and-run tactics, replicating rapidly before the full immune response manifests. While the immune system eventually combats the virus, the damage is already done. Fever, therefore, plays a pivotal role in the immune system's multifaceted strategy, exerting pressure on pathogens from multiple angles. However, the question remains: if fever is so beneficial, why do we attempt to suppress it when ill? Should you fight fever with medication? Should you fight fever with medications? It is common to believe in quick-acting remedies, yet over-the-counter medications like aspirin or ibuprofen were only widely available and affordable in the past century. Seeking pharmaceutical relief for a headache is a relatively modern concept in human history. Pain, though unpleasant, serves a purpose by signaling the body to conserve energy and rest. This is not a flaw but an adaptive feature of the immune system. Pain and fever are closely linked, and medications such as ibuprofen and paracetamol also target fever. In children, fever is frequently managed by concerned parents or healthcare providers, often due to misconceptions that fever itself is the disease or fears of long-term harm. Generally, fever below 40 degrees Celsius is not hazardous and does not require intervention. However, exceptions exist, particularly for vulnerable populations like pregnant women, the elderly, or those with weakened immune systems, where the added stress of fever could be dangerous. Fever exceeding 40 degrees Celsius is perilous for anyone, as it often indicates a malfunction in the body's internal thermoregulatory system. The situation becomes more complex in severe diseases. There is evidence that fever-reducing drugs may not expedite recovery from conditions like influenza or chickenpox. However, ethical dilemmas in clinical research complicate these findings. In one study, administering strong anti-fever treatments to critically ill patients led to increased mortality, highlighting the risks involved. Overall, there is strong evidence suggesting that individuals may benefit more from retaining their fever when battling serious infections. Moreover, there is limited clinical data supporting the notion that suppressing fever improves health outcomes. Nonetheless, exceptions exist, such as in cases involving neurological injuries or strokes. Further research is essential. Thus, the decision to combat fever hinges on weighing potential benefits and risks. If the fever is not dangerously high and you can endure it, allowing your body to maintain this natural defense mechanism may accelerate recovery. However, if you feel severely unwell and are otherwise healthy, taking medication to alleviate pain and fever could provide relief at the cost of slightly reduced immune efficacy. Ultimately, consulting a healthcare professional is advisable, as online information should not dictate medical decisions. The choice to manage fever is inherently about balancing these trade-offs. If a fever is not life-threatening and you are able to cope with it, you are reinforcing your body's defenses and potentially accelerating recovery. Conversely, if you are in significant distress and generally healthy, medication may offer quicker relief, albeit with a minor compromise to your immune response. Regardless of the path chosen, the next time you experience a high fever and discomfort, you can take solace in the knowledge that your adversaries are facing even greater challenges.